Hello.
Um, so Dr. Schilm is from Fraunhofer IKTS, and they specialize in ceramic technology. They're in the beautiful Dresden. Although I'm not sure if you are in Dresden now, because I heard some conversation in the background. But yeah, and yeah, so we're gonna now hear about solid-state batteries and the development of co-sintered ceramic material. So the stage is yours, and to the audience, please ask questions. So good luck.
So, also from my side, a warm welcome, remote welcome. Welcome to my talk, Solid State Batteries and the Development of Co-sintered Ceramic Materials. So, with a view on on the last talk, we had a really nice introduction on the development of solid state batteries, and now we will go to the outer edge of the timeline, and we will present some results on our recent development of ceramic or oxide-based solid electrolytes and so-called co-sintered composite electrodes or cathodes. So, and first, I want to present some fundamental. I will make a fundamental comparison of solid-state battery and the lithium-ion batteries, and with a view on the left side of the slide. You are mainly familiar with a setup of a conventional lithium-ion battery. It's not to explain there in detail, but if you view on a model of a solid-state battery, there are some really important differences. So maybe you have the cathode, which need to have a solid electrolyte, which can be a polymer, a sulfide, or even an oxide. The separator needs to have a certain function. It needs to be dense. It needs to be highly ion conducting to enable the use of metallic lithium as a high dense energy density anode material. Yeah, and so if you go away from the liquid electrolytes and go to the solid electrolytes, you have three options to use. The polymers are most established on the market, as we have heard in the last talk, the monorecas. Sulfides are coming up, and as they are good processable at room temperature, they have high conductivities. But there are also some oxides, main ceramic sintered materials. They can have potential advantage over the other both classes of materials, as they are for better compatibility to lithium metal, which should be used as an anode material, and they have a high potential for good compatibility at high cell voltages. Yes. However, what is the state of the art in case of all ceramic solid state batteries without use of polymers and sulfides? Here we have an example which has been developed by the Forschungszentrum Jülich on the left side. It's an all ceramic solid state battery, which is the feasibility has been demonstrated in a nice way. But in fact, as you see here, the cathode material on the top, the cathode layer is quite thin in comparison to the separator. And this means that you have quite low volumetric energy density. Because of the thickness, even the absolute conductivity decreases of the separator. They use the lithium metal as an anode material, and the famous LiZO solid electrolyte material is stable against these anode material. Um, so it's here that on the left side, on the right side, there's a graph that shows you a chart on the development of the specific power and energy density compared to sulfide-based solid-state battery with the oxide phosphate-based solid-state battery in comparison to the lithium-ion battery. We will see that the ceramics will have some potential advantages over the other ones. But besides the LLZO solid separator material, the ceramics, there's another system we are working on. It's a known, you have it probably heard before. It's a so-called LATP. It's not a pure oxide, it's a phosphatic material, which has an advantage that you have the high mechanical stability and a high hardness, and you can achieve ion conductivities up to 1 millisiemens per centimeter at room temperature. It is quite stable at under atmospheric conditions.